living systems are the most complicated thing we know about in the entire universe. They have to be studied with these multidisciplinary approaches. We have collaborations to work on the biomechanics of insect flight, for example. And you might wonder why I study insect flight. Because tiny organisms with brains smaller than a pinhead can navigate a complex three-dimensional environment and find food and find mates, and they're, in many ways, an ideal model for how we might design flying miniature robots.
The Defense Department is fundamentally interested in not just autonomous systems and autonomous robotics, but they're also interested in devices that may help injured warriors. People who have suffered limb loss, who have suffered brain damage and have mobility disorders. Disorders of movement include muscular dystrophy, multiple sclerosis. So to move around in space requires acquisition of a huge amount of information.
The challenge then becomes how do all the parts fit together? How do they work? And that's a big data problem. I would say that access to large data sets doesn't just change the speed with which science is done, it changes the kinds of questions that you can ask and answer. So we have information theorists who are in faculty in the Department of Biology. It's a very collaborative, open, interdisciplinary culture fostered by the kind of people that we hire. The resources that are most important to biology are human capital.
We need scientists who are willing and easily able to delve deeply into multiple disciplines. So I need people who are comfortable with mining giant data sets, but I also need people who know how to get the data.
What is scarce is brilliant people who like to collaborate in teams, and that's the kind of person we're looking for.
I'm an oceanographer, and I study the microbes that live in the ocean. I think of them as the planet's great recyclers. The oceans really dictate many of the large-scale features that happen on our planet. The oceans are changing rapidly. So what does that mean for our future? Understanding those processes is important for this large-scale issue. Understanding how the oceans work on a smaller scale is important for people's livelihoods. In the past, oceanography was really dominated by seagoing activities. Over the last decade, we have moved into a world where we have sensors on the seafloor, autonomous vehicles that can move through the ocean, collecting huge amounts of data. So we have moved from sort of a data poor field into a data-rich environment. The data that we generate in all these different ways are noisy. They're multidimensional. The importance of this is being able to integrate across these different kinds of data sets. That's where the richness will come from, and that's where the real advances. Being able to integrate across the data sets, you can ask questions that you never were able to do before. Because oceanography is so important on these global scales, we have collaborations that go across the campus. Some of our very important collaborations are with computer scientists, statisticians, with the eScience group on the UW campus. If I had to say the one direction that would greatly advance my research is this idea of being able to integrate the data, to have access to the best minds that are doing that. That is an area that's huge, and so it's got lots of both human infrastructure and actual computer infrastructure. That's a resource that is vital across our campus.
What we work on is building the telescopes and instruments that we use to produce digital maps of the night sky. Today, we work on a project called the Large Synoptic Survey Telescope, the LSST. The LSST will image half the sky every 3 nights, so it has a 3 billion pixel digital camera on the back of the telescope. And over a period of 10 years, it'll mass about 100 petabytes of data. And so today, when we start having data sets that are hundreds of terabytes or hundreds of petabytes in size, it means that you can ask any question of the data. Instead of having to go out to the telescope, you effectively have the telescope sitting on a computer. And by making this data available to the public, It means that anyone can ask those questions. But to manage that data means that you have to work with computer scientists. So it could be a computer scientist, it could be a biologist who has a different way of thinking about patterns within data, who can make the next fundamental discovery. Yeah, then one of the really great things that I find about the university is there are almost no barriers for collaboration across departments. We collaborate with statistics and computer science. What would make a fundamental difference to the astrophysics program here would be to bring in new postdocs, new graduate students, and be able to fund them to work on research that is looking 5 years into the future, as opposed to research where we're just looking at the next step, 1 year from now. The second aspect is when I'm working with hundreds of petabytes of data, the scale is so much larger that we need the facilities to be able to support that as well.
Engineering is about making the world better, making the world a better place and making people's lives better, and computer science is at the center of both of those things.
What's happening in science is that it's shifting from kind of a data-poor enterprise to a data-rich enterprise.
So one of our goals is to be at the center of the data-centered world and to provide the technologies that drive science and that drive business.
Scientists have been sort of hungry for acquiring new data, but that's not really the bottleneck to discovery anymore. We actually have quite a bit of data, and the new bottleneck to discovery is being able to analyze it.
We're all awash in data, but it's very difficult to know, given enormous amounts of data, how to process it, how to store it, how to visualize it, how to mine it for information.
It's not just businesses who have data, and it's not just users accessing this data through well-designed interfaces. Now everyone has a lot of data. Astronomers, biologists, oceanographers, they all have just huge amounts of data.
The challenge used to be gathering the data. Now the challenge is extracting knowledge from that data.
They want direct access to the data. They want to ask questions, get answers quickly, and that is really transformational to how we build data management systems. We want these systems to process large amounts of data and also be easy to use.
The way I think about the role of computer science in general is what we're doing now is putting the smarts into everything. Smart homes, smart cars, smart bodies, smart discovery. Smart discovery is every field of discovery. The sciences and social sciences and some of the humanities are swinging from data poor to data rich. If you want to study the formation and evolution and dissolution of social cliques, you used to pay a bunch of undergraduates $6 an hour to participate in a focus group at lunch. And now you're trying to get your mitts on 1 billion users worth of Facebook data.
What scares me a little bit is I imagine that there are labs out there that are choosing which kinds of questions they want to work on, and they might be steering themselves away from questions that involve large data sets because they don't have the capability to sort of work with them. And so what I'm worried more about is that we don't actually know the extent of the problem, that we're actually self-selecting towards research questions that are safer or more traditional or easier to do.
We are trying to grow. We're under a lot of pressure from the state to grow.
That requires not just faculty and students, it requires professional research scientists. The ability to have more postdocs in this data science area would make an enormous difference to our impact and our ability to move forward quickly. If we don't lead in data science, then we're not going to lead in any other field, because every other field that I can think of requires that the scientists working in that field have access to the absolute latest, absolute largest scale data analysis techniques.
Definitely having resources to push this data science to the next level will continue to be transformational to our campus and make sure that we are the leaders.